is the keyword, right? And you are given some ciphertext. I have it here. Okay. So this is something like. Okay. So R. I'm going from left to right of what is given. So this is R. First of all, you have to find the length of the ciphertext. It's 20 characters, right? The length of the ciphertext is 20 characters.
Yeah.
And Mandarin is 5 characters long, so 5 columns. So the number of rows is going to be
I got it.
divided by 5, so that's going to be 4 rows.
I got it at the very end.
Okay? So fill up this,
Oh, this tight.
the first 4 rows, and then you see this is the order. A, break the tie left to right. Third is this. And then again break the tie left to right. So this is 4th and 5th.
Oh, I put the letters wrong.
Okay? So this is NICR, then ASN.
I did it right.
STIX. So you should not stop here, you should write what's the plain text. So what's the plain text? Transposition cipher. Okay, so
Oh, you had to write the words out too?
yeah. You should go, you have to tell me how you read the thing. So you read row wise. Okay?
You're going to get some points there, right?
Yeah. So the last one is the dummy character. Alright, for the undergrads there was this cryptanalysis, which means I could ask for the grads next time. I didn't ask for the grads this Caesar cipher cryptanalysis. It is little bit trial and error, but not much. There are only 2 possibilities. And I saw some people did it. So this is the ciphertext. So what should be, or what is there you could try? And you know it's Caesar cipher, right? So that's given to you. Okay. Okay, so you could try first before that. Yeah, M or E, but this is ciphertext. So what would be the possible plain text for this M or E? A or I, right? Those are only 2 standalone words in English, which means only 1 character forming a word. Right? So it could be either this is an I, this is an I, and since it is a Caesar cipher that's given to you, right? If this is I, this has to be an A. Right? And since again it is a cipher, this is I, this has to be an I. So try with that and try to decrypt this part. Before that you have to find what? The shift value. Okay? So try the shift values. If E is substituted with I, remember always the relationship is what? Ciphertext is plain text plus key. So what is the key? Ciphertext minus P. So here ciphertext is I minus C, minus E. So what is that? I is going to be
4.
I is not 4.
I is 9.
I is 9. Okay,
Yeah.
good, you have it.
I'm saying 4 the answer.
And E is what?
5.
5. So this is 4.
Right? So B is 4 and the answer is 5.
E is 4, the answer is 5. Try to decrypt this. This is the ciphertext, right? I think I did wrong. This is the ciphertext. This is the ciphertext and this is the plain, trying to find the plain text, right?
Right.
So the ciphertext is E minus I. So E is going to be what?
4.
4 minus I is
I is 8, sir.
8.
Yeah.
So this is negative 4. So if you get negative 4, you have to add a 26 to it. So that is going to be 22. So this is a possible shift value. I'm not telling this is the shift value. This is a possible shift value. So what you have to do, you have to try to decrypt the rest. So this is what? 24, right? No, 23, right? 23 minus 22,
There's one.
right? No, you're trying to find the plain text, yes. Ciphertext minus key, right? So this is x minus the key, which is 22. So x is what, 23, 22, that's going to be 1. So this is going to be some a something, so I'm not going to spend much time. It won't make sense. Try to decrypt it, it won't make sense.
One is B.
Huh?
One is B.
B? Yeah, one is B.
Okay.
Oh yeah, one is B. So it won't make much sense. Alright? So which means the opposite, you don't even need to try. Which means this should be an A and this should be an I. And if that is an A, this should be an A. And a two-letter word in English starting with A could be am or an. But since you know this is I, it cannot be an. So if you know grammar, right? So then, so this has to be am. So then we are almost there. So just find the key value and decrypt this. So you should get what? Yeah. So I am a tennis player. Okay. I am not. I like tennis also. So that is one thing you have to know. Then explain why shorter messages are more secure substitution. I did tell you that in class, right? Why shorter messages are still better to go, like it's not...
You can't analyze it.
Right. So why shorter messages are still okay to go through substitution-based encryption? Because if you have a very short message, say even Jackson State University, right? Or let's say Jackson, that's a short message. If you look at the distribution of the percentage distribution, what is the most commonly occurring character in English? E. And that is like what, 12% of the time?
Yeah.
So it seems some people have memorized that.
Or
Okay. There's no even E appearing even once here. So which means you can't really find the statistics of this short message and compare it with that. Right? So it really adds some confusion. So even though it's a short message and we're going through some substitution cipher, you cannot use this English statistics. So it is okay to use substitution ciphers for shorter messages. Just plain simple substitution ciphers. Okay? Alright, so the others are DES, which we did in class, right? Going through 4 cycles and showing it is the same as the first input, and the meet in the middle attack, that's what it is, right? You don't have to try 2 to the power, because if you think you have to use, this is 56 bits, this is another 56 bits, right? So totally it is 112 bits, but because of the inherent flaw in the double DES, right? What is the flaw in double DES?
You don't use it.
You encrypt with one key and then further encrypt with the second key. Right? So if you follow a consistent notation, let's say I do this, so this is encrypt with the second key. But what is the attack? It's a known plain text attack, isn't it? So it's a known plain text attack means what? The attacker has access to the ciphertext as well as to the plain text, but not the key. So you're trying to find the key K1, K2, right? So what is the strategy? The attacker has the plain text, he has a ciphertext.
on both sides.
So look at this thing. You could do one level of decryption by guessing a key K1, right? And K1 is only 56 bits long. And guess another value for key K2, which is another 56 bits long. So you could do, you could encrypt P with K1, get an intermediate ciphertext, okay? So encrypt this with K1, and decrypt this C with K2. So if both intermediate texts are same, the ciphertext, which means you have found the right K1 and K2, right? You encrypt the plain text once with K1 and decrypt the ciphertext with the other key K2. If the two ciphertexts match, the intermediate ciphertext match, which means you have found K1 and K2. And since K1 and K2 are each only 56 bits long, and on average you could find them 2 to the power 56 over 2, right? So 2 to the power 55. It takes 2 to the power 55 attempts on average to find each key. So totally you have to spend 2 to the power 55 plus another 2 to the power 55, which is 2 to the power 2 times 2 to the power 55, which is 2 to the power 56. So that's why it takes only this much time, not 112, 2 to the power 112 times. Okay? And then the ranking of the substitution ciphers. So which one creates more confusion or most confusion? Vernam cipher creates a maximum confusion. Why? Because you generate a key that is as long as the message, and the key is really random numbers generated. Okay. So by confusion, again, what we mean? If I substitute, say, again, let's pick up apple. So if I substitute for P with K, for the other P, more likely it should not be K, it should be some other character. So that's what is the confusion, because if an attacker manages to find one mapping that K is a substitution for P, then he cannot say what is the other, if he sees a K somewhere downstream, he cannot say that the corresponding plain text is P, it should be something else. So you create confusion by having different mappings for each for every occurrence of plain text character. One instance of plain text character substitutes something else, other instance it substitutes something else. So that's what creates confusion. Whereas Caesar cipher is the other extreme because it has a constant shift value, which means every character is shifted by the same shift value. So which means if you are shifting P to K, this P is also shifted to K, which means E will be shifted to something else. It won't be shifted to K, it will be something, say M or whatever the shift value is. So which means what? Once you find a shift value, like you did the cryptanalysis for this problem, once you find the shift value, you can do it for every character in the ciphertext. So it doesn't create any confusion at all. So Caesar cipher is the least confusing cipher. And what else? Virginia cipher does create some confusion, but the flaw, or not the flaw, the weakness or the drawback with that is the key is not as long as the message, as in Vernam cipher, right? So if you have, say, a long text, as in plain text, your key could be, say, a word or a phrase from a dictionary, right? So it cannot be as long as the message, most likely. So which means what? Let's say if the key is security, like one of your sample problem, then you have to repeat that security until you reach the end of the message. Which means if you encrypted, say, K with S, all you do is simple addition, right? Plain text plus key ciphertext. So K plus S will give you some ciphertext. If somewhere else downstream, if you encounter another K, you have to do K plus S, which means the two ciphertexts have to be the same. The character, the two ciphertext character, right? So if an attacker manages to find such a pattern, okay, so he can do some successful cryptanalysis. So even though it creates some confusion because some characters are replaced with different characters every instant, but not all the time. Okay, so that's what Virginia cipher is. Last one is monoalphabetic cipher. What does monoalphabetic cipher do? That's the first few slides. The key is actually this mapping from the plain text to the ciphertext. So which means A is mapped to a D, B is mapped, it could be any mapping. This is just an example. Okay? So if you see this encryption, wherever I occurs, you replace with W. Wherever F occurs, you replace with I. Okay? Wherever W occurs, you replace with R. So that mapping is fixed. Even though the shift value is not a constant, it could be each character is shifted by different shift values. This mapping is the key. Okay, so how this could be broken, or how someone could find this mapping without going through a brute force approach of 26, because the map, how many mappings you could have? You have 26 characters, right? So I can map 26 characters to another set of characters, this many permutations, but you don't have to try this many permutations. How could you break? That could be another question, right? I think there's one in the question back. Why you don't have to try this many times? Provided the message is a long message, what can you do? You can do an English analysis. You can find the frequency distribution of the characters, right? If you find the frequency distribution of the characters, and if you have done substitution cipher, this is a substitution cipher, right? So what will be the case? We know that, where's the chart? E appears 12% of the time, which means if you use monoalphabetic substitution cipher, what should appear 12% of the time in the cipher text? Huh? Yeah, because E is in the plain text. If it is the plain text, it should appear close to 12% of the time. But here you are substituting E with F. So as a cryptanalyst, you have access to what? The cipher text. So you substitute the cipher text to this language frequency analysis, find out the distribution of each character in the cipher text, and get the percentage distribution, and compare that with the chart that you have for the standard English. So since E is replaced with F, F should appear, F should have a percentage distribution of something close to 12%. Similarly, T, which has close to 10%, instead of T you should see U appearing close to 10% of the time, right? Because T is substituted for U. So if you could find such mapping, then you can right away come up with, if the percentage distributions match, then you can come up with this mapping, right? So all you have to do is this frequency distribution analysis of the characters in the cipher text. Okay? So that is actually another answer for one question in the question bank. How would you, let's say you have a cipher text and it was generated either through a simple substitution cipher or a permutation, which is transposition based cipher, right? Those are the simple algorithms we saw. The substitution cipher, which is like Caesar cipher and all those stuff, and transposition cipher, what is that we saw? Columnar transposition, all the permutation based cipher, right? Isn't it? These are the two broad classes we saw. So given a ciphertext, how would you find out whether it was generated through a substitution based cipher or a permutation based cipher?
Through the letter count.
Again, through frequency analysis, right? What is the inherent mechanism behind substitution? With substitution you want to create confusion, right? And with transposition we are doing what? Diffusion. So if it is a transposition based cipher, just simple transposition, not like DES, you do all combinations and things like that, just a simple, say, columnar transposition. If you find the frequency distribution of the characters in ciphertext, you should get what? The same distribution that is there for standard English, provided again the message is quite long, right? Because with diffusion, what happens? The characters are just moved around. You are not substituting one for the other, right? So if you do a frequency distribution of the characters in ciphertext, it should get something close to this. Clear? Actually, that's the undergraduate project, project 1. If you have gone through the project description, you have to find the frequency distribution and decide which one it is, whether if one is like either a substitution or a permutation in cipher. Okay? I don't think anybody has gone through undergrad. You have to read the project description. Okay. So that clearly tells you if the percentage distribution matches with this is a diffusion based or transposition based cipher. If it doesn't match, it could be, it's not diffusion, it could be substitution. And it could be like Caesar cipher if there is an exact shift based mapping or like monoalphabetic cipher. But if it's Virginia cipher or Vietnam cipher, it's confusion. So you cannot clearly say what is substitution. But you can at least say it is some substitution based cipher, because if it has been a purely transposition based cipher, you should get the same frequency distribution. So you kind of, that's how a crypt analyst could narrow down to what algorithm it is. If, say for example, he doesn't know what algorithm has been used to generate ciphertext, he just gets access to the ciphertext. He cannot try all possible algorithms in the world, right? But with this test, he can just omit one category of algorithms. Once he finds a frequency distribution, he can conclude whether it's transposition based or substitution based, and just go with one category.
So for shorter messages, it's better to go with substitution.
Right, that's what the other question is, because for shorter messages, even it's better to go with transposition because the frequency distribution will not match.
You said better to use transposition for this?
It's either way is fine, but what his question was, he thought it's better just use substitution. My answer was, you could use anyone, because for a shorter message, if you find the frequency distribution of Jackson, you won't get this distribution, right? So you cannot conclude it's diffusion based. But substitution ciphers are generally considered weaker in the sense that whatever we saw so far, right? We cannot use Vietnam cipher all the time because it's just random number gen based. So Virginia cipher is the best bet we have. Monoalphabetic is weak, Caesar cipher is weak, right? So substitution based ciphers are generally considered weaker compared to permutation based cipher. Okay? Like Caesar cipher or even Virginia cipher or monoalphabetic could be used for shorter messages because it's difficult to find. The confusion is there and you cannot find the shift value by computing this frequency distribution. Okay? Clear? Okay, so I think that covers pretty much most of this. So we can come back again for another 2 weeks or 3 weeks. We have what, on September 26th. September 26th is your first exam, which will include this module cryptography and what we are going to do operating system security, and if we can cover something on the next module. The next module is going to be software security and things like that. Okay, so you have to get serious. If not, you are already serious. Okay, so you're already in the 4th week of the semester, so you have to start reading. So the first project is out there, so it's due when? Right, 1 week from now. Okay, so I'll post the second project soon, sometime for the weekend. It will be mostly, I'm not sure yet, so probably something to do with operating systems and we think about it. Okay, so how many of you have taken operating systems, either undergrad or grad? Already. So how many of you have not taken? Okay, if you have been taking now, it's fine. Alright, so some of these concepts will cover directly from operating systems, like segmentation, paging, and all those stuff. So I'm not going to spend much time. So we are going to look at from a security point of view again. So what's the purpose of having operating systems? Any quick definition why we need operating systems? Huh? Computation? Protection. Protection from what?
Doesn't the operating system run the computer?
They need operating system on a computer, right?
Right.
Okay, that's you're getting somewhere to that because a computer is hardware based, right? So as a human, you don't really want to work directly on hardware. Okay, so you want some interface between the user application and the hardware. Okay, so that's the kind of purpose of operating system. So it's kind of like a middleman. That's a quick definition of it. But as we said, you want to kind of, once that is there, you want to protect the resources of the computer. Okay, so especially nowadays you're working on what? Multi-programming, multi-user, multitasking, all these fancy names. Multi-user means what? You have a server in which multiple people have accounts, and multitasking could be like all your machines, like you could do several things on a computer. You could open a web browser, you could or do
Different
some,
applications.
huh?
That's a different
Yeah, you could run multiple applications, right? So, multiple processes, that's the term you should use. So, all these things will access different parts of your computer, okay? So, even files, so you may have one file which you don't want some other user to access. Even among your processes, you don't want certain processes of users to access some files of the other processes, right? So, you want some protection, okay? So all this access control, so we start using all these terms, have to go through this operating system. So the operating system checks whether a user or a process can do certain things or not. Okay, similarly memory management. I'm sure everyone knows the operating system runs or is loaded in the main memory, right? You know the main memory, the RAM and the hard disk and all this stuff, right? So when the machine is turned off, the operating system is located where?
In the case?
When the machine is off, right, it's not running, where is the operating system? In the hard drive. So when you turn on the machine, the operating system is loaded from the hard drive to the main memory. And your user applications are also running in the main memory on the RAM, or stored in the RAM, right? The address space of all your processes. So there is a certain space in your RAM allocated just for your operating systems. And there is certain space allocated just for a user process. Okay? So we call them as address space. Okay? The memory allocated for every process or operating system. So if you want to do some computation within your process, you should not touch the space of, you should not try to write something to the memory space allocated to the operating system. Right? So if you're trying to write, most likely your system will crash if you do something that is really not acceptable for the system, right? So the operating system should check every time the user is trying to write to memory, you should check whether it's trying to write to the valid location or not. Okay? So if you run some C programs, you will get this famous segmentation fault. So one reason is because, especially if you use pointers and all those stuff, you get that error because you are trying to write to some memory location to which you are not allowed to write. Okay? So all these things are some of the main responsibilities of the operating system. So we are going to see these 5 topics in detail: memory address protection, user authentication, okay, and people try to log in. How do we check for that? And access control. Okay. So there are 2 things. Authentication means trying to validate a user who is trying to log into a system. Access control comes after you authenticate. So different people have different permissions. So for example, if you take a POS as an example, I could log into POS, you could log into POS, people above me could log into POS, chairs, administrators, right? But as a student, you could do certain things. As a faculty, I could register you for courses and certain things. As a chair, they could force you to certain kinds which I cannot do. So each user has certain permissions. Okay? So everyone can log in. First of all, that should be validated, whether you have an account or not. But not like everyone who logs in can do the same thing. Okay? So you can log in, I can log in, but each of us can have different permissions to do. So that is what is access control. Okay? So checking for the permissions of the user, of an authenticated user. Okay? Then file protection is really like trying to, when you are again trying to store a file or write to a file, okay, you check for all these things. So we'll see more as we get into it. Virtualization is a kind of new buzzword that is coming up, some cloud computing and all those stuff. So we'll look something about virtual machines, what are different ways you could do virtualization and things like that. Okay. Okay, so the first part should be quite straightforward. You you have seen in architecture and operating systems. This is something familiar, this kind of diagram, right? So, as I said, the address space of a process is basically the memory portion, the region of memory allocated to a process when it is running. Okay? So, process, as you know, the standard definition from operating system is what? A program in execution, right? That's a standard definition. So, when you run a process or a program, it should be allocated some address space, which means memory in the RAM or the main memory. Okay? That's called the address space. Now, the address space of a process is generally divided or could be composed of these 5 sections. Okay? And memory is linear. Okay? So, you have a low-end memory and then a high-end memory. So, the memory addresses could be ordered. You know that memory locations are accessed by using addresses, right? 32-bit address or 64-bit address, all those things. So you could order, this is a low-end address, this is a high-end address, okay? So one address appears after the other address and so on, okay? So it's a very linear ordering, there's no hierarchy or anything, okay? So if you look at this, among these 5 regions, the stack is always the high end of a process address space and this is the lower end, okay? So what are those 5 regions? We will come back to this when we look at buffer overflow attacks, more of that, especially the stack and the heap. But now let's just look at what each portion contains. The text portion contains actual executable code, the machine code of your program. Okay? The data portion contains the static variables which are initialized to some initial value. This BSS portion, block standard by symbol, contains static variables that are not initialized, which means variables which are just declared and not initialized or initialized to 0 by default. Okay. These two are what is of interest to us, the heap and stack. The first 3 are allocated fixed space. Okay. Whereas the heap and stack are allocated dynamic space, which means there is a maximum space allocated to them, but they are not completely used. Okay, so this is a